We often speak of the Milky Way as if we know it. We refer to it in textbooks, imagine it in illustrations, and describe it in sweeping spiral beauty. But the truth is, we do not actually know what our own galaxy truly looks like. We are inside it, yes, but that very fact makes it one of the hardest objects in the universe to observe. It is like trying to draw a map of your entire house while trapped in one of its windowless rooms. We do not know exactly how many stars there are. We do not even agree on the shape of its spiral arms. Is it 2 or is it 4? Some estimates say 100 billion stars, others 400 billion. This uncertainty is not due to a lack of effort. It is due to our perspective. Gas clouds, dust, and the plane of the galaxy itself obscure our view in almost every direction. But that veil is slowly being lifted. Thanks to missions like the GAIA Space Observatory and infrared surveys from telescopes such as VISTA, astronomers are now piecing together the most complete and dynamic map of the Milky Way ever attempted. In this video, we will journey through this data. We will uncover hidden stars, witness galactic cannibalism, trace cosmic shockwaves, and explore the mechanisms that shape galaxies across time. The Milky Way is alive with stories, and we are finally beginning to hear them. We live inside a galaxy that stretches more than 100,000 light-years across and holds billions upon billions of stars. We call it the Milky Way. Yet despite its colossal presence, we do not truly know what it looks like. That may sound strange, but imagine standing inside a vast forest and being asked to draw the shape of the forest itself. You can look around, see the trees near you, perhaps even glimpse some distant light through the canopy. But the full structure remains hidden. That is exactly the challenge astronomers face when studying our home galaxy. Some of the most basic facts about the Milky Way remain uncertain. How many stars does it contain? Estimates range from 100 billion to as many as 400 billion. What shape do its spiral arms take? For decades, scientists have debated whether it has 2 major arms or 4. These are not minor details. They speak to the very structure and history of the galaxy that cradles our solar system. The trouble lies not in the questions themselves, but in the point of view from which we are forced to ask them. We are embedded deep within the Milky Way's disk, like trying to read a sentence from 1 millimeter above the page. What blocks our view is not distance alone, but dust. Interstellar clouds of gas and particles fill the plane of the galaxy, absorbing and scattering visible light. Toward the galactic center, this matter becomes so dense that it forms a region astronomers call the zone of avoidance. In optical wavelengths, this region is almost opaque. Light from stars beyond it is obscured or lost entirely. It is a blind spot, vast and inescapable, right at the heart of what we wish to study. The result is a kind of cosmic irony. We can observe distant galaxies across the universe more clearly than we can observe our own. And yet, despite these challenges, we continue to reach. With instruments that see in infrared, radio, and X-ray, With spacecraft orbiting far from Earth's atmosphere, and with the help of powerful computational models, astronomers are slowly peeling back the layers. Each new mission brings us a little closer to understanding the galaxy we call home. But as of today, our map of the Milky Way is still incomplete, still blurred at the edges, still filled with mystery. It is a sobering thought that after centuries of stargazing, the most elusive galaxy may be the one we are inside. To truly understand the Milky Way, one must know more than where the stars are. One must know how far they are, how fast they are moving, what they are made of, how hot they burn, and how bright they shine. All of this information, when gathered precisely, allows us to build a three-dimensional map, not a static picture, but a dynamic model of our galaxy in motion. That is exactly what the GAIA Space Telescope set out to do. For more than a decade, GAIA observed the heavens with one singular purpose: to measure the positions and properties of over 2 billion stars with a precision never before achieved. The key to GAIA's mission lies in a phenomenon known as parallax. It is a simple but powerful effect. When you change your viewpoint, nearby objects appear to shift relative to those farther away. You can see this for yourself by holding a finger in front of your face and alternately closing one eye and then the other. Your finger appears to move back and forth. Now imagine using the entire orbit of Earth around the Sun as a baseline instead of the space between your eyes. That is what GAIA does. It uses the changing perspective from one side of Earth's orbit to the other to measure the tiny shifts in a star's apparent position. This principle allows GAIA to determine the distance to each star with astonishing accuracy. The closer a star is, the more it appears to move against the background. The farther away it lies, the less it shifts. But GAIA does not just observe a star once. It returns to each star dozens of times over the years, tracking not only its position, but also its motion. From this, GAIA calculates not only how far away a star is, but how fast it is moving and in what direction. When combined with data on brightness and color, this creates a full astrophysical fingerprint for each object in the sky. GAIA does not use a single telescope, but two. These are positioned at a fixed angle from one another and share a massive camera with nearly 1 billion pixels. This dual system allows GAIA to observe two parts of the sky at once, slowly spinning to trace wide arcs across the heavens. Its sensors are so sensitive that they can detect motion as small as a human hair seen from 1,000 kilometers away. And its radial velocity spectrometer measures the subtle Doppler shifts in starlight, tiny changes in wavelength that reveal whether a star is moving toward us or away from us, and how fast. Over the course of its 10-year mission, GAIA collected more than 3 trillion individual measurements. These data points were not just stored, they were processed, calibrated, and refined into usable catalogs of cosmic information. 3 major public data releases have already taken place, one in the year 2016, another in 2018, and a third that was released in 2 stages across 2020 and 2022. Each release represented a significant leap in quality, as more time allowed for better parallax measurements and clearer motion patterns. The scale of Gaia's map is almost incomprehensible. It includes the position and motion of over 2 billion stars, but also records detailed information about their temperatures, luminosities, surface gravities, and chemical compositions. With this wealth of information, astronomers can trace stellar families, reconstruct ancient galactic mergers, and identify stars that were born together millions or even billions of years ago. GAIA's data extends beyond the Milky Way as well, cataloging distant quasars, nearby asteroids, and even satellite galaxies. It is not just a map, it is a living history of the sky. Because of Gaia, astronomers can now simulate the motion of stars both backward and forward in time. They can rewind the galaxy to see how it was shaped by past collisions, or fast forward to witness the future motion of stars across the Milky Way. In some of these simulations, stars form flowing streams, clumps, and ribbons, ghostly traces of ancient galaxies that were torn apart and absorbed. Gaia does not merely show where stars are now, it tells the story of how they arrived there. In doing so, it has transformed our understanding of the Milky Way from a blurry silhouette into a high-definition time-lapse. But even the most remarkable missions must eventually come to an end. On January 15th of the year 2025, Gaia took its final observation. The cold gas propellant that kept it stable in space, used at just 12 grams per day, had finally run out. It is now undergoing final calibrations before its systems are permanently powered down. Yet its legacy is far from over. 2 more massive data releases are still to come. One of them, expected in the year 2026, will contain over 500 terabytes of new information. And the last, data release number 5, will complete the full 10.5 years of Gaia's extraordinary journey. That final catalog may hold answers to questions we have not yet dared to ask. It might be easy to think of galaxies as isolated islands of stars peacefully spinning through space. But that is not how the universe works. Galaxies interact. They pull on each other with gravity, collide, distort, and sometimes even devour one another. Our Milky Way is no exception. In fact, it is a cosmic cannibal. Hidden within the motions of its stars are the fingerprints of galactic collisions, of ancient mergers that shaped what we see today. And thanks to the Gaia mission, we are now able to trace the evidence of these violent events. Among the 2 billion stars observed by Gaia, researchers discovered a peculiar group, about 30,000 stars that did not quite belong. These stars were moving in the opposite direction from the majority of stars in the galaxy. Their chemical compositions and colors were also distinct. It was as if they had a different origin entirely. When scientists ran simulations to explain these patterns, one answer emerged again and again. These stars were not born in the Milky Way. They were the remnants of another galaxy, one that our own had absorbed long ago. This ancient galactic collision likely occurred between 8 and 11 billion years ago. The devoured galaxy has been given a name, GAIA Enceladus. Some call it the GAIA sausage, due to the elongated shape of its stellar distribution. The stars it brought into our galaxy still follow similar orbits, forming a kind of fossil structure buried within the larger body of the Milky Way. This merger may have been responsible for many of the features we observe in our galaxy today, including the thick disk and perhaps even the central bar that spans the core. But GAIA Enceladus was not alone. It may have had a smaller companion, another dwarf galaxy called Aruya Sequoia. Some researchers believe these two galaxies were part of a binary pair that fell into the Milky Way together. Their combined mass and gravitational disruption would have caused waves through our galaxy, altering the orbits of stars and possibly triggering new star formation. Like cosmic ghosts, their remnants are scattered throughout the halo of the Milky Way, each one a silent witness to an ancient collision. GAIA data has since revealed that the Milky Way may have consumed not one or two, but as many as 6 separate galaxies throughout its history. These mergers have left behind more than just stellar streams. They have altered the very shape and motion of the Milky Way itself. The outer edges of the galaxy appear warped and uneven, like the ripples on the surface of a disturbed pond. These distortions are not random. They are the echoes of impacts from long-dead galaxies, each one merging, dissolving, and becoming part of something larger. And the process is not over. One of our closest neighbors, the Sagittarius dwarf galaxy, has collided with the Milky Way 3 times in the past 5 billion years. It is currently in the process of being torn apart by tidal forces. Its stars are slowly being stretched into a glowing arc that wraps around the Milky Way, and it is expected to merge completely in the future. Interestingly, some astronomers believe that the last impact from Sagittarius may have disturbed enough gas to trigger the birth of our Sun 4.5 billion years ago. These stories, buried in the movement of stars, are only possible to reconstruct because of missions like GAIA. The Milky Way is not a static structure. It is a living, evolving entity, built from the remnants of many smaller galaxies. What we see today is a tapestry of ancient violence, stitched together over billions of years, and it may only be the beginning. As we continue to study our galaxy in greater detail, we may find more hidden galaxies that once danced too close and were swallowed whole. The Milky Way is not just our home. It is a monument to cosmic appetite. As remarkable as GAIA's achievements are, its vision has one critical limitation. GAIA sees the universe in visible light, the same narrow band of wavelengths our human eyes perceive. And within that spectrum, much of the Milky Way remains cloaked in darkness. Thick lanes of interstellar dust stretch across the galactic plane, blocking visible light and hide in countless stars from view. This is why, even with a map of 2 billion stars, large portions of our galaxy remain invisible. To see deeper, to see through the dust, astronomers needed another kind of eye. Enter VISTA, the Visible and Infrared Survey Telescope for Astronomy. Located at the Paranal Observatory in Chile, VISTA operates not in visible light, but in the near-infrared. This gives it the ability to penetrate the veils of cosmic dust that obscure our view of the Milky Way's central regions. Using a powerful infrared camera known as VIRCam, VISTA has spent over a decade capturing the hidden heart of our galaxy. The result is the largest and most detailed infrared survey of the Milky Way ever completed. Between the year 2010 and the year 2023, VISTA observed the night sky across 140 separate nights, collecting nearly 200,000 images and generating 500 terabytes of data. This survey, known as VVV, the VISTA variables in the Via Lactea, was later extended into a second phase called VVX. The phrase Via Lactea is Latin for Milky Way. Together, these twin surveys unveiled regions of space previously unreachable with visible light. Infrared light is key to this breakthrough. While visible light is easily scattered and absorbed by dust particles, infrared light can slip through those clouds, revealing stars and structures hidden behind them. The difference is astonishing. Take, for instance, the Trifid Nebula, a well-known cloud of glowing gas and dust. In visible light, it appears as a pink and blue swirl, with its core obscured. But in the infrared, VISTA revealed an entire swarm of stars shining clearly through the fog, some lying even beyond the nebula, on the far side of the galaxy. In one remarkable image, astronomers discovered two faint stars behind the Trifid Nebula. They turned out to be classical Cepheid variables, a type of pulsating star that brightens and dims in a regular rhythm. These stars are of enormous value because their pulsation period is directly linked to their true brightness. By comparing their intrinsic luminosity to how bright they appear from Earth, astronomers can determine their distance with precision. In this case, the Cepheids were found to be 7 times farther than the nebula, lying far beyond the galactic center. But these two were only the beginning. Using the full VISTA dataset, astronomers identified over 650 candidate Cepheid variables near the center of the galaxy. Among these, 35 were found to be classical Cepheids, young, hot stars less than 100 million years old. That was a surprise. The galactic bulge, long thought to be home only to ancient stars, was hiding something unexpected. These youthful stars traced a thin, almost invisible stellar disk stretching through the center of the galaxy, undetectable in visible light, but now revealed in infrared. This discovery challenged long-held assumptions about the structure of the Milky Way. The central bulge was believed to be a relic of the early galaxy, formed from ancient stars during a time of intense mergers. Yet, here was a population of relatively young stars, aligned in a flat disk, suggesting continuous star formation across the galactic midplane for at least 100 million years. And there may be even younger stars still hidden in the data, too bright for VISTA's detectors, waiting to be revealed by future surveys. What this shows is that the Milky Way's inner regions are far more dynamic and complex than once believed. The discovery of a young stellar disk within the bulge means that our galaxy is not merely a collection of ancient parts, but a place of ongoing transformation. Through the power of infrared astronomy, VISTA has peeled back the curtain on a region long shrouded in mystery. And in doing so, it has rewritten a part of our galactic history, revealing that star formation in the heart of the Milky Way may have never truly ceased. VISTA's success is more than technological, it is philosophical. It reminds us that the universe does not always appear as it truly is. What we call dark may only be hidden. What we assume to be old may contain seeds of new creation. The galaxy we live in is not static, but alive, shaped by forces both visible and unseen. Thanks to infrared eyes like VISTA, the secrets locked within the dust are beginning to come to light. And each discovery brings us closer to understanding the Milky Way, not just as a structure, but as a story still unfolding. Hidden behind the dusty shroud of the Milky Way lie some of its oldest and most enigmatic inhabitants, globular clusters. These are dense, spherical collections of stars, often containing hundreds of thousands of suns packed tightly together. They orbit the galaxy like ancient satellites, forming a kind of halo around its core. Most globular clusters are more than 10 billion years old, born when the universe itself was still young. And until recently, many of them were invisible to us, concealed behind curtains of interstellar dust. That was until VISTA looked deeper. Using its infrared vision, VISTA uncovered what visible light could not. In the year 2011, astronomers discovered two previously unknown globular clusters. The first was found near the known cluster UKS-1, a faint red smudge in visible light. But VISTA's images told a different story. In the upper corner of that same field, another tight knot of stars appeared, designated VVVCL 00001. Soon after, another globular cluster, VVVCL 00002, was revealed. Both had been hidden in plain sight, just beyond the reach of conventional telescopes. What made these discoveries remarkable was not just that they were hidden, but where they were found. One of the clusters lies surprisingly close to the galactic center, making it potentially the nearest known globular cluster to the core of the Milky Way. In a region thought to be dominated by younger, brighter stars, this ancient stellar relic had gone unnoticed. And perhaps even more intriguing is the possibility that VVCL 00001 and UKS-1 may be gravitationally bound to each other, a rare pairing of binary globular clusters within our own galaxy. Binary globular clusters are incredibly rare. We have seen them in other galaxies, such as the Large Magellanic Cloud, but never before confirmed within the Milky Way itself. If future analysis shows that these two clusters are indeed locked in a gravitational dance, it could shed light on the processes that form massive clusters like Omega Centauri. When globular clusters collide or merge, they may seed the growth of truly giant stellar systems, ones that blur the line between cluster and dwarf galaxy. But globular clusters are not the only secrets VISTA has uncovered. Beneath the dust, a different kind of cluster emerges: open clusters, also known as galactic clusters. These are looser groupings of stars, often younger and less densely packed than their ancient cousins. VISTA identified at least 96 new open clusters in the central regions of the Milky Way. Each one is a stellar nursery, or a family of stars that form together and are slowly dispersing as they drift through the galaxy. Their discovery expands our picture of the Milky Way's stellar architecture in remarkable ways. One such open cluster, VVVCL00003, lies 15,000 light-years beyond the galactic center. It was the first of its kind discovered on the far side of the galaxy. Unlike globular clusters, which remain tightly bound, open clusters are often transient. Their stars eventually drift apart, leaving only the memory of their shared origin. Finding these clusters is like discovering snapshots of the galaxy's ongoing formation, brief moments frozen in time. And thanks to infrared astronomy, we are now able to witness those moments even in the most obscured corners of the Milky Way. Together, these discoveries of hidden globular giants and fleeting open clusters reveal a galaxy teeming with structures we could not see before. Each cluster, whether ancient or newborn, carries with it a story of formation, of motion, of transformation. With VISTA's help, we are not just mapping the Milky Way in greater detail, we are uncovering its forgotten history and its ongoing evolution. What once lay in darkness is now visible, reminding us that even in the most shadowed places, the stars still shine. In the early days of radio astronomy, scientists began mapping the night sky not through light, but through radio waves. At first, they detected signals from familiar sources, stars, galaxies, and nebulae that were already known. But soon, something strange appeared. Dotted across the sky were powerful radio sources with no visible counterparts. Through optical telescopes, these locations showed only faint, star-like points. They were not galaxies, not stars, and yet they emitted enormous amounts of radio energy. They were labeled quasi-stellar radio sources, or quasars. The name quasar reflected the mystery. These objects looked like stars, but behaved like something far more powerful. For years, their true nature remained unclear. They were incredibly small in size, at least in appearance, yet they outshone entire galaxies. What could produce that much energy from such a compact region? The answer did not come quickly. It took decades of observation, theory, and debate. And when the answer finally came, it reshaped our understanding of the universe itself. Quasars, it turned out, were not stars at all. They were the brilliant hearts of active galaxies. At the center of almost every galaxy lies a supermassive black hole, millions or even billions of times more massive than the Sun. Most of these black holes are dormant, quietly pulling in matter from their surroundings. But in some galaxies, a vast amount of gas and dust spirals into the black hole, forming a hot, spinning accretion disk. As matter in this disk rubs together and compresses, it heats up to incredible temperatures. The result is a blinding outpouring of light across the entire electromagnetic spectrum, from radio waves to X-rays. This is what we see as a quasar. The light from a quasar does not come from the black hole itself. Black holes, by definition, emit no light. Instead, the light comes from the violent, chaotic environment just outside the event horizon. In some quasars, intense magnetic fields channel some of this infalling matter into narrow, high-speed jets that shoot out from the poles of the black hole. These relativistic jets travel at nearly the speed of light, extending for hundreds of thousands of light years. Even from billions of light years away, they can be seen blazing through the cosmos. Quasars are among the brightest objects in the universe, capable of outshining all the stars in their host galaxies combined. Some are so luminous that their light has traveled for over 10 billion years to reach us. And because of that, quasars offer a glimpse into the distant past, a time when galaxies were young and the universe was dense with gas. Once mysterious and misunderstood, quasars are now understood to be the signatures of cosmic giants, supermassive black holes in the act of feeding. They are not stars, but the beacons of galaxies devouring their surroundings at unimaginable scales. While quasars shine from the distant reaches of the universe, there exists a smaller, quieter version of them much closer to home. These are called microquasars. Unlike their supermassive cousins, microquasars form around stellar mass black holes, objects only a few times the mass of the Sun. They do not sit at the centers of galaxies, but instead form within binary systems, where a black hole orbits a companion star. Under the right conditions, material from the companion is drawn in, forming an accretion disk and sometimes even launching relativistic jets, just like in full-sized quasars. One of the most famous microquasars ever discovered is SS433. Located roughly 18,000 light-years away in the constellation Aquila, SS433 is a binary system consisting of a massive star and a black hole. As the black hole feeds on material from its companion, the infalling matter heats up, generating intense radiation and producing powerful outflows of plasma. What makes SS433 truly remarkable, however, are its jets. These jets do not just move fast, they move at a quarter of the speed of light, creating one of the most extreme environments ever observed in our galaxy. The jets of SS433 are also unusual in their structure. They are not fixed in place, but precess, sweeping out a cone in space like a spinning top, wobbling as it turns. This motion creates a corkscrew-like pattern as the plasma flows outward, and it provides a rare opportunity to study jet dynamics in real time. Observations across radio, optical, and X-ray wavelengths show two distinct jet regions, an inner region that extends only a few light years, and an outer jet that stretches over 300 light-years from the system. The mechanism that drives such enormous acceleration remains a subject of intense study. Recent research suggests that these jets are powered by shock waves and intense magnetic fields near the base of the accretion disk. As electrons are accelerated to near-light speeds, they interact with surrounding photons, transferring energy through a process called inverse Compton scattering. The result is a burst of high-energy gamma rays. In fact, some of the gamma rays from SS433 have been measured at energies exceeding 10 trillion electron volts, making them among the most energetic particles ever detected from a stellar system in our galaxy. SS433 is more than a curiosity. It is a natural laboratory. Because it is located within our own galaxy, astronomers can study its behavior in much finer detail than is possible for distant quasars. It offers a miniature version of the same powerful processes seen near supermassive black holes, and in doing so, helps unlock the secrets of how jets form, how particles are accelerated, and how matter behaves under extreme gravity. In the story of cosmic engines, SS433 is a rare glimpse into the mechanics of black holes, not just swallowing matter, but violently hurling it back into space. One of the most intriguing mysteries in high-energy astrophysics is how electrons can reach such extreme velocities, close to the speed of light, near black holes, and in jets like those from microquasars. In systems like SS433, electrons are thought to be accelerated by powerful shock waves formed near the base of the jet. These shocks are produced when streams of material moving at different speeds collide, compressing and energizing the plasma. As charged particles cross the shock front again and again, they gain more and more energy, in a process known as diffusive shock acceleration. But these high-speed electrons do not keep their energy forever. As they race through space, they encounter lower-energy photons, particles of light from surrounding stars, or from the accretion disk itself. When a high-energy electron collides with one of these photons, it can transfer some of its energy to the photon, boosting it to much higher frequencies. This process is called inverse Compton scattering. It is one of the key ways gamma rays are generated in astrophysical jets, converting kinetic energy into powerful radiation visible across the universe. In Section 433, scientists have observed that the highest energy gamma rays tend to emerge closest to the base of the outer jets, where the electrons are most energetic. Farther out, the gamma rays become weaker, as the electrons gradually lose energy over time. This spatial distribution supports the theory of inverse Compton scattering and shock-driven acceleration. What begins as a swirl of infalling gas becomes a high-speed river of particles and light, shaped by gravity, magnetism, and the chaotic physics of extreme environments. In this way, black holes become engines, not just of destruction, but of cosmic radiation. Among all the quasars ever discovered, one stands alone in both scale and mystery. It is called TON 618. At its heart lies a supermassive black hole with an estimated mass of 66 billion times that of the Sun. By itself, this black hole is more massive than most galaxies. It is located so far away that the light we see from it today began its journey over 10 billion years ago. That means we are observing TON 618 as it existed when the universe was less than 3 billion years old. And that raises a difficult question. How did something so enormous form so early? Black holes grow by feeding on surrounding matter. The more they consume, the larger they become. But that growth takes time. For a black hole to reach the mass of TON 618 in only a few billion years requires either a head start, perhaps from a massive primordial seed, or a feeding rate far beyond what is typically observed. This leads to one of the major puzzles in modern astrophysics. According to our current models of black hole growth, there should not be enough time or material for such massive quasars to exist so early in cosmic history. And yet, there they are. One possible explanation is observational bias. The brightest quasars are the easiest to detect, especially at great distances. This is known as Malmquist bias, the tendency to observe only the most luminous objects in a given range, while dimmer ones remain hidden. It may be that there are many smaller black holes out there, but they are too faint to spot from across the universe. In this view, TON 618 is not necessarily an outlier in its time, but simply the most visible member of a much larger, invisible population. Another explanation lies in the nature of the early universe itself. During its first few billion years, the universe was filled with dense clouds of gas, raw material that could be quickly drawn into black holes. Galaxies were smaller, closer together, and collided more frequently, funneling matter toward their centers. Under these chaotic conditions, some black holes may have entered runaway growth, becoming quasars in a relatively short time. As the universe expanded and matured, the available fuel diminished, and with it, the number of active quasars declined sharply. Today, quasars are rare. None have been observed within 500 million light-years of Earth. That does not mean supermassive black holes are gone. They are still present at the centers of galaxies, including our own. But without large quantities of gas to feed on, they remain quiet, dark, and invisible. TON 618 is a relic of a wilder time, a monument to the violent, energetic youth of the cosmos. Its existence challenges our theories, and its light reminds us that the early universe may have been far more dynamic than we ever imagined. Galaxies are not static structures. They are living, evolving systems that change in shape, color, and structure over billions of years. From elegant spirals to featureless ellipticals, the form a galaxy takes can tell us a great deal about its history and future. Just as stars are born, grow old, and die, so too do galaxies follow a path of transformation, one guided by time, gravity, and the raw material of the cosmos. Understanding this journey reveals not just how galaxies form, but how they fade. The story often begins with spiral galaxies, beautiful, flat disks filled with gas, dust, and young stars. Their arms wind outward from a bright central bulge, forming symmetrical patterns of light and motion. These spirals are among the most recognizable and photogenic structures in the universe. In them, we see vibrant star formation, triggered by density waves that compress clouds of gas as they rotate through the galactic disk. The result is a tapestry of star-forming regions, glowing pink and blue with hot newborn stars. But this level of activity cannot last forever. Over time, the gas and dust that fuel star formation is gradually consumed. Some galaxies experience bursts of intense star formation, so-called starburst events, where rapid stellar creation exhausts the available material in only a few 100 million years. One striking example is Messier 61. This galaxy, viewed nearly face-on, blazes with red hydrogen regions and glowing blue clusters. It sits in the crowded Virgo cluster, where gravitational interactions likely triggered its starburst. As the supply of cold gas dwindles, the spiral arms begin to lose their definition. The galaxy dims, and the hot blue stars fade as they burn out. What remains are older, cooler stars, yellow, orange, and red in color. The once vivid arms blur into the surrounding disk. This transitional phase gives rise to lenticular galaxies. These galaxies still resemble spirals in outline, but lack the youthful glow of ongoing star formation. One such example is NGC 4921, sometimes referred to as an anemic spiral for its faded appearance. Lenticular galaxies bridge the gap between spirals and ellipticals. They retain their disk-like shape, but are largely devoid of gas and dust. Star formation has slowed to a crawl, and the galaxy takes on a smooth, pale complexion. In galaxies like P-G-C 10922, spiral arms are barely visible, ghosts of a more active past. Their light is dominated by older stars, and their central bulges often swell in size. Without the chaotic dance of stellar nurseries, their evolution is guided by slow gravitational dynamics and time. Eventually, the disk itself thickens and begins to lose its structure. The stars move in more randomized orbits, no longer confined to a flat plane. The final stage in this journey is the elliptical galaxy, a smooth, rounded collection of stars with little or no internal features. Ellipticals come in various sizes, from dwarf spheroids to massive giants. One such example is Messier 105. It is dominated by reddish light, and new stars are exceedingly rare. In some of these galaxies, only one sun-like star may form every 10,000 years. It is not only internal processes that shape this transformation. External influences also play a major role. Galactic collisions and mergers can destroy spiral structure and redistribute stars into new shapes. When two galaxies merge, their gas may be consumed in a final burst of star formation before settling into an elliptical form. These violent encounters leave scars, shells, ripples, or faint tails of stars flung far from their original orbits. Over time, these features fade, and the new, merged galaxy begins its quiet decline. As galaxies age and evolve, they also grow redder. This is because older stars dominate their light, and there are fewer new blue stars being formed. The color of a galaxy, just like its shape, becomes a signature of its evolutionary stage. Spirals tend to be blue, lenticulars pale or yellowish, and ellipticals a deep, dusty red. Through color alone, astronomers can estimate a galaxy's age and its level of star-forming activity, allowing them to piece together the grand narrative of cosmic change across the sky. From the glowing spirals of the early universe to the silent ellipticals of its distant future, galaxies embody the long arc of cosmic time. They begin as vibrant, star-forming structures, grow through collisions and consumption, and eventually fade into stillness. Each phase of their life tells us something about the forces at play across the cosmos. And as we observe galaxies at all stages of evolution, we glimpse not only their stories, but our own, written in starlight, scattered across billions of years and trillions of stars. Not all galaxies follow neat classifications like spirals or ellipticals. Some defy structure entirely. These are the peculiar galaxies, cosmic outliers shaped by violence, distortion, and transformation. Many of them are found in the ARP catalog, a collection of the most unusual and chaotic galaxies in the sky. Compiled by astronomer Halton Arp in the mid-20th century, this catalog contains galaxies torn by collisions, stretched into tidal tails, warped into arcs, or tangled together in gravitational embraces. These forms are not mistakes. They are evidence of galaxies in the act of change. Among the most striking are ring galaxies, cosmic bullseyes formed when one galaxy punches through the center of another. The impact creates a ripple effect, triggering a circular wave of star formation that radiates outward like a splash in water. Hoag's object is a famous example, with a nearly perfect blue ring surrounding a yellow core. Others, like the Cartwheel Galaxy, show more turbulent motion and twisted arms. These are not peaceful systems. They are the aftermath of high-speed collisions, and their symmetry masks the chaos that created them. Some galaxies form mysterious shapes, like the letter X, or vast arcs of stars disconnected from any clear core. These are often the result of gravitational interactions and mergers that warp the original disk into strange configurations. One such system, known as the X-shaped galaxy, shows twin trails of stars curving outward from a central bulge, as if frozen mid-spin. These structures may arise when two galaxies with aligned disks merge, twisting their stars into new paths under intense gravitational forces. In the universe, even destruction can produce beauty. But not all peculiar galaxies are large. Some are small and dense, so dense they challenge the line between galaxy and star cluster. One of the most extreme is M60 Ultra Compact Dwarf 1. It contains hundreds of millions of stars packed into a space only a few hundred light-years wide. For comparison, that is more compact than some star clusters, but far more massive. Astronomers believe it may be the remnant core of a much larger galaxy that was stripped of its outer stars in a violent merger with a more massive neighbor. These peculiar forms remind us that galaxies are not isolated. They pull, tear, absorb, and transform one another over cosmic timescales. Gravity acts as both sculptor and destroyer. Collisions do not simply destroy galaxies, they reshape them, creating new structures, igniting waves of star formation, and sometimes leaving behind only the dense, compact cores. Each odd shape in the sky is a snapshot of a longer dance, one that may end in silence or begin anew in another form. In this way, the universe writes its history not just in stars, but in the scars they leave behind. The story of the Milky Way is far from complete. What we know today of stars, clusters, mergers, and dark matter is only the beginning. Each new observation opens more questions than it answers, but the future of exploration is already taking shape. The GAIA mission, which has given us the most detailed star map in human history, is preparing to pass the torch. Plans for a next-generation GAIA, with sharper vision and deeper reach, promise to unlock structures and motions we have never seen before. The current GAIA has mapped more than 1 billion stars, tracing their motions, brightness, and distance with exquisite precision. But even this is only a fraction of the galaxy's full population. Many stars remain hidden behind dust or lie too faint to detect. The next generation will push further into the obscured regions of the galactic core, the halo, and the distant outer arms. It will peer into the infrared, see through the clouds, and track the orbits of stars with micro-arc-second precision, resolving structures on scales smaller than a grain of sand held at arm's length. This will not be a solo effort. Future missions, both in space and on the ground, will work alongside GAIA's successor. Telescopes like the Vera Rubin Observatory will scan the entire sky repeatedly, catching motion and variability across time. The James Webb Space Telescope will continue to peel back the veil on the early universe, finding quasars and galaxies at the edge of time. Together, these instruments will link the large-scale structure of the universe with the detailed choreography of stars inside our own galaxy. With each new generation of data, we move closer to answering profound questions. How did the Milky Way assemble? What is its ultimate fate? Where is most of its matter hidden? And could stars like our Sun, circling silently through the galactic disk, carry life beyond Earth? Future missions may map exoplanets, search for biosignatures, and even detect gravitational ripples from mergers between massive black holes. The Milky Way is not just a place of stars, it is a laboratory of time, motion, and possibility. The next generation of GAIA will not just see deeper, it will think faster. With advances in artificial intelligence, machine learning, and real-time data processing, we will no longer wait years for maps to unfold. Instead, the galaxy will reveal itself almost as it moves, and in doing so, it will become not a distant object of study, but a living system, one we are part of, and one we are beginning to understand. The future of galactic exploration is not just about seeing more, it is about seeing with new eyes. The universe is not finished. It is still unfolding, still revealing secrets hidden in the light of distant stars and the silence between them. Every discovery, each faint signal from a dying quasar, each trembling motion of a star, peels back another layer of cosmic history. We are not merely observers looking into the past. We are participants in a story that is still being written. A story of gravity, of energy, of time itself stretching outward toward futures we have not yet imagined. What once seemed like distant chaos now takes shape as structure. Behind the veil of dust, through the distortion of dark matter, within the glow of ancient galaxies, we begin to see patterns, spirals, filaments, collisions, birth and decay, woven together in a grand design. Yet even as we chart these forms with greater clarity, we feel the edge of the unknown. The more we understand, the more questions bloom. What lies beyond the Milky Way's edge? What came before the first stars? Where is the universe heading next? In this vastness, we are small, but not insignificant. We carry curiosity, precision, and the relentless urge to ask. The universe is not finished revealing itself, and we are not finished listening. With every new telescope, every new theory, every new glimpse into the dark, we come closer to seeing not just where we are, but what we are part of. The stars continue to speak. The galaxies continue to move, and somewhere, deep within the quiet, the next revelation is already on its way. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.